So this next topic is going to be on graphing trig functions, and we're basically going to be given a function rule, and then we're going to sketch a graph of what that would look like. So the first example is f of x equals -2 sine x plus 1. So in the previous unit, we talked about these 5 key points for every single trig expression. You have to remember those, okay? What I typically do, and what you'll see me do in every single example, is I'm going to sketch the original function, or in this case, the parent function. So the parent function for this one is sine, okay? And if we think back, sine is increasing through the origin, and we have our 5 key points, okay? So the 5 key points for sine, or I guess we can just call this y, because we're going to be transforming it, are going to be, this was at negative pi, this was at positive pi. And we have equal length input value intervals, so that means slicing through the middle was 0, and then cutting those intervals in half, we had negative pi over 2, and then we had pi over 2. Okay, so the inputs, and I draw a sketch so that I can see, okay, what is the function doing? We're going from 0 to -1, 0, +1, 0, okay? So at negative pi, we're at 0. We cross the midline 3 times. At negative pi over 2, we're at -1. Pi over 2, we are at 1. So you have to make sure that you can at least get this far so that we can get to the transformations and then get to the sketch from there, okay? So if you need to review those key points, make sure you go back to the Unit 11 videos to look at those. All right, so just like we did in transformations for Algebra 2 and then what we did in the first semester, we are going to dissect the transformations from our function rule and then apply them to the inputs and the outputs. So for this one, we can see that x is isolated. We do not see a b value. We do not see a c value. Therefore, there are no input transformations. There are no domain transformations. So I'm going to go ahead and move this over a little bit. That way we have more space. All right, so now I'm going to work my way out, and then I'm going to look at my range transformations. So think of the transformation map. We're looking at this one. F of x is equal to a sine. We'll have b, and then remember you want your x isolated minus c plus d. And then the only part that will be changing is what trig expression are we looking at, okay? So remember your a's are going to change your range, and your d's will change your range, and then your b's will change your domain, and then your c's will also change your domain, okay? In this case, we only have an a and we have a d, but we also have this third transformation, which is that vertical reflection. So we're going to multiply the y values with -2 and then add 1 to them. So we have a vertical dilation with a scale factor of 2. We're stretching out the sine function, so we should see it grow vertically. And then we're also shifting the entire sinusoidal curve up 1, okay? So that's what we're going to be doing to the range values. Plug in 0, we get +1. Plug in -1. -2 times -1 is 2. And then from there, we'll add 1, so we get 3. And 0 will repeat, so I can just, you don't need to do so much mental math. So we can just plug a 1 here. And then from here, plug in 1, you get -2 plus 1, so we end up with -1. All right, so we'll go ahead and get a sketch of this. Based on the values, it looks like we're still centered on the y-axis, but we shifted the curve up, all right? So I'm going to make sure I have more space above the x-axis. So we're still at negative pi, positive pi, and then negative pi over 2, and positive pi over 2. And then we'll be at -1, +1, and then 3. Do your best to make sure that the ticks on the graph are equally spaced. I think my left side's a little more compressed, but it doesn't need to be perfect. Just do the best you can. All right, so when I sketch this, I have negative pi and 1. And then negative pi over 2 and 3. And then 0, 1. Pi over 2, -1. And pi 1. And then we'll include curve in there. So do the best you can to show that concavity, your point of inflection in there within that snapshot. As we get X and Y transformations going, you'll end up with 4 columns. If you want to scratch out the ones you're not using, you can go ahead and do that. It makes it a little bit easier to extract them from your table to apply them to the sketch. All right, so I think that is it for this one. If you look at my notes and my key, I went ahead and found the domain, found the range, the period, the frequency, the amplitude, and what was the other one? The midline. I found all of that. I'm not going to do that in this video just because there's other videos that are specific to that. Plus, it would make it like 45 minutes long. Okay, so that is the sketch for sine. Next one is going to be cosine. Okay, so now that I know I'm working with cosine, now that I know I'm working with cosine, I want to think, okay, what does cosine look like, the parent function? It's going to go through like this. So we have that maximum, point of inflection, minimum, and then on the other side, point of inflection, minimum. And just like sine, we are starting at negative pi and going to positive pi. So our transformation table will have those same equal length input value intervals. So for the inputs, we'll have negative pi over 2, 0, pi over 2, and pi. And then for the outputs, I can see that I'm starting at a minimum, so negative 1. Go ahead and notate that. And then at negative pi over 2, we're at 0. At 0, that's the maximum on the y-axis. Pi over 2, we're back at the midline. And then at pi, we are at negative 1. Okay, I really need you guys to be careful with this, okay? Because I don't want you to go straight to the transformation table from here. You have to factor first, okay? And we talked about this in Algebra 2. We talked about this in first semester, that in order to see the true transformations, you need to factor out that leading coefficient. Now, our b value is 2. That's not going to change. What's going to change is the shift, okay? We need to factor out that 2 so we can see the true phase shift, okay? So we have cosine. We'll factor out the 2, and now I have x plus. So whatever you factor out, just multiply that constant with the reciprocal of it. So we'll have pi over 2 times 1/2. That will give me pi over 4. So that my actual phase shift is pi over 4, not pi over 2. Okay. So always isolate the x value. Okay. So with this one, this is on the flip side from sine. For sine, we had all transformations that affected the y values, the range. For cosine, we have transformations that affect the domain or the x values. But remember, for domain and x values, we're basically undoing those actions because we're using them twice. We use them for the input, and then it's also being used to change the outputs, which it's because they're in the input. So we're going to use the reciprocal of 2, which is 1/2, and then we're going to subtract pi over 4. Because that translation is actually pi over 4 to the left, not to the right. All right, so we'll have 1/2 x minus pi over 4. All right, and then I'm going to shorten the y side a little bit since we don't need it. All right, from here, we'll substitute each value in. So I have 1/2 times negative pi. That's going to give me negative pi over 2 minus pi over 4. So negative pi over 2, it will be negative. We need a common denominator for 4, so we'll multiply pi over 2 with 2. So we'll end up with negative 2 pi over 4 minus pi over 4, which gives us negative 3 pi over 4. All right, next we'll substitute negative pi over 2. So I have, that should be times. That looks like a minus, but that's multiplication. So we'll have 1/2 Oopsie, I should not have had a pi in there. That should be a 1 right there, so 1/2. And then that should be just a 2. So we get 2 pi over 4. Nope, that should be 2 pi. Sorry, because we're multiplying. Okay, so let me rewind. Getting ahead of myself. So for this one, for negative pi, I'm substituting in for x. So, oh, I really got ahead of myself. No, I didn't. We're good. It's just the notation here. I wrote this incorrectly. So this should be -1 or -1/2. Oh, I see what I did. I combined them. Okay. So we'll have negative pi over 2 minus pi over 4. So that was a minus, not a multiple, not multiplication. And then multiply with 2 over 2, so we get negative 2 pi over 4 minus pi over 4, which gives us negative 3 pi over 4. Okay, sorry about that. All right, so now let's plug in negative pi over 2. So we're going to substitute negative pi over 2 in for x. 1/2 times negative pi over 2, we get negative pi over 4. And then we're going to subtract pi over 4. We already have a common denominator, so we're going to end up with negative 2 pi over 4, which simplifies to negative pi over 2. So we get negative pi over 2. So you have two options from here. You can either keep substituting in and simplifying and manipulating, or you can look at the relationship to this interval here. Because these are equal length input value intervals, we can go ahead and conclude that we are going to increase the domain by pi over 4. Because from negative 3 pi over 4 to negative pi over 2, the distance is pi over 4. And because these are equal length input value intervals, all of the other distances will also have to be pi over 4, because this is a sinusoidal curve. It's repeating, it's oscillating, therefore they will be the same, okay? So if I do negative pi over 2 plus 1/4, I get negative pi over 4. If I do negative pi over 4 plus 1/4, or the 1/4 is also pi over 4, I get 0. If I do 0 plus pi over 4, we get pi over 4. So really the fun fraction time is going to be with the first two, and then after that you can just use the interval from there, okay? All right, so now we can go ahead and sketch our graph. I'm going to go ahead and clear out the middle column because I don't need it, but we have to keep the y one because we didn't transform it. Therefore, we will use the original outputs. So for my sketch, it looks like we're mostly in quadrants 2 and 4. So I'm going to go ahead and move it over a little bit. And we're still centered at the x-axis. So we'll be at negative 3 pi over 4, negative pi over 2, negative pi over 4, 0 and pi over 4. And then positive 1, negative 1. So if I sketch this, I'm at negative 3 pi over 4, negative 1, negative pi over 2, 0, negative pi over 4, 1, 0, 0, pi over 4, negative 1. So we'll concave up, concave down, and concave up. And then now we have our sketch for cosine. All right, moving on to tangent, we have 1 plus tangent 3x. If we think about our transformation map, we see that 1 in front. We don't see that usually, but it's just additive, so it's just that plus d being pushed to the front. So it'll have the same effect. It's still a vertical translation. Don't let that trip you up. But we'll go ahead and rewrite it as tangent 3x plus 1, just so that it aligns with our transformation map. So for tangent, quick sketch is going to be increasing through the origin. and then we'll have 2 vertical asymptotes. So those vertical asymptotes are the first and last key points, and then we'll have 3 key points that are on the curve itself. All right, so key points for tangents. If we think back, this is at negative pi over 2, and then we're going to positive pi over 2. So negative pi over 2, positive pi over 2. Right in the middle of that will be 0. And then equal length input value intervals. This will be negative pi over 4, positive pi over 4. And if we look at our sketch, we'll have a vertical asymptote at the beginning and the finish. And then in the middle, we will have 0. And then again, the outputs will be -1 and +1. And since it's increasing, we should see -1, 0, +1. Okay, so now this is the first example where we are not either only changing the domain or only changing the range. We now are changing both, okay? So let's start with the domain transformations. We have a b value of 3, which means we have a vertical dilation with a scale factor of 1/3, or just a horizontal compression. So we are taking our tangent function and we are squeezing it by a factor of 1/3, which means we need to multiply that with 1/3. Okay, so we'll have 1/3 times x. Oh, that's the only, okay, we only have one. So let me go ahead and squeeze that in. Get it? Squeeze. Okay, and then I'll scoot this over. That way we have more space. All right, sorry, those are the next door neighbor dogs. Hopefully they quiet down soon. So now we're going to apply the transformations for the y values, which is just 1. So now we're taking our tangent curve and we are shifting it up 1 unit, which means I should see that point of inflection shifted up to +1 on the y-axis. Okay, so we'll just do y plus 1. Vertical asymptotes, it's like infinity plus 1, it's still infinity. Vertical asymptotes will not change based on any type of transformations when we use vertical transformations. They only change using domain transformations. And then -1 plus 1 is 0. 0 plus 1 is 1, and then 1 plus 1 is 2. And I clearly got distracted, so let's go ahead and do our input values. So 1/3 times negative pi over 2, that will give us negative pi over 6. 1/3 times negative pi over 4, that will give us negative pi over 12. So now I can see the trend here, right? We are going to be at 0, and then pi over 12, and then pi over 6. So if you notice, we don't have a phase shift, right? And tangent is odd, which means we have rotational symmetry. So I should see these be the same values, they're just negated since we still have that rotational symmetry about the origin. All right, drawing this sketch, we are still centered at the y-axis, but we are mostly in quadrants 1 and 2. So I'm going to zoom in more to those quadrants. Negative pi over 6, negative pi over 12, and then pi over 12, and then pi over 6. And then we'll have 0, 1, 2. So when I sketch my vertical asymptotes, I'm going to have a vertical asymptote at negative pi over 6, and then another at pi over 6. Sketching the key points, we're going to be at negative pi over 12, 0, 0, 1, and I keep looking at other key points. So I'm going to go ahead and white those out. And then we're at pi over 12, 2. And this should be increasing, and we should see concave down, and then switch to concave up, and they should be approaching the vertical asymptotes. All right, so that is the first 3. The next video will have the reciprocals of those, so you'll see cotangent, cosecant, and secant. Hope this helps.